I'm here with Chris Ferrie. Chris, thanks for joining me.
Thanks for having me.
Let's talk about quantum computing. One of the most well-known use cases of quantum computers is cryptography. It's sort of well understood that that's a use case by the general public. But I think there are many things that are not well understood. I've always wondered, once we get sufficiently large and robust quantum computers that will be able to crack our foundational encryption methods that we use today, does this mean that existing encrypted content on the internet will no longer be safe in the future?
I mean, I think that's true regardless of whether quantum computers exist or not. So this kind of cartoon imagery we have of encryption is with like a lock and key, but it's not like physically impossible to decrypt a message. It's encoded with a math problem. And if you have a big enough computer or enough time with pen and paper, you can always solve this problem. So yes, with a quantum computer, we think we can solve the problem faster, but it's not as if, quantum computing is some magical key that unlocks current encryption. It can just solve those problems we think are keeping our secrets safe a lot faster. Now, anyone with the algorithm and enough time and a big enough computer can crack any message. You can set your computer churning away. It may take hundreds of years, thousands of years, depending on the level of security that message has. But you will crack the message eventually. It's just quantum computers, we think, will be able to do it faster.
Yeah. I mean, I guess then it depends on just how much faster versus brute forcing it with classical computers, because, if we believe it will be substantially faster, so fast that most encrypted content is basically unsafe, then it does pose the question, should we be using any of these classical encryption methods at all for stuff that ends up on the internet publicly if it's sensitive material? How much faster do you think we can get with quantum computing?
Well, it really depends on the problem. I think in terms of encryption, it's not, we usually differentiate speedups between what's known as polynomial or exponential. Mm-hmm. But the reality is there's problems that are somewhere in between. If you had the magical box, the quantum computer, and it worked perfectly, then it would be, in for all intents and purposes, instant for the kinds of encryption we do today. But for other problems that quantum computers could potentially be used for, it's a more modest advantage. And then, of course, there are problems for which we think quantum computers just won't be useful for at all.
Yeah, I guess the concept of quantum computing, it has been in the public consciousness for many years now, and I think it's not very well understood by the public which problems it is good for and which it isn't. I mean, there is a lot of hype. There are even books coming out by people who are not quantum computing experts in recent times, sort of opining on the the changes to come. One area that is often cited that happened relatively recently was when researchers at Google made a bold claim that they had achieved something called quantum supremacy, which is a bit of a scary term, with their Sycamore machine. Can you describe what happened there, and if you feel this represents sort of truly meaningful advances in quantum computing? Yeah,
so it's not as impressive as it sounds, so I'll get that out of the way. It is what they've done is technologically impressive. It's certainly a step up from what we had previously, and certainly vastly superior to what we were doing a decade ago. But the entire concept of quantum supremacy is a bit problematic, because it gives you this picture that there's this kind of black and white boundary between quantum and classical, when in reality it's just this big gray area. So now, and certainly at the time, it was like trying to define a line between black and white in this giant field of gray. So yeah, that's why there was at least some controversy about what it was they achieved. The idea is basically you want to find a problem for which, a quantum computer could solve that problem in some reasonable amount of time, for which no conventional computer, which we call classical computers, digital computers, could solve, given all of the computing power that we have, and and the age of the universe, or some long but finite amount of time. So if you could find such a problem, then you would say, well, look at, clearly the quantum computer is now something vastly superior to digital computers. But there isn't this kind of step transition, right? So the kinds of problems that we're looking at and the devices that we're building, it's more of this really gradual increase in capability, and where you draw the line is somewhat arbitrary. So what they had said that they achieved was they could do something, their device could do something that it would take the world's fastest conventional supercomputer thousands of years to solve. What it actually did was not useful for anything. It was they basically created some target random distribution and said that the device could sample numbers according to that distribution, whereas a classical computer would take a long time to figure out how to get it perfect to sample that distribution. So it's somewhat arbitrary problem. So I mean, for us in the community, our point of view is usually something like, "Wow, that's a great scientific achievement. Probably shouldn't have used that that phrasing, because it even though you can't blame them directly, they must have known that it was going to be misinterpreted." Yeah. But maybe that's what they wanted, right? That's what gets press.
Well, it is an incredibly highly cited paper that they put out. Do you feel like it is at least a stepping stone towards meaningful progress? Meaningful progress en route to something like commercial scale quantum computing?
I don't know. I think these papers, these research papers that come out, they'll be lost to the annals of academia at some point in time. Like, nobody will care when we transition from 4 to 5 qubits, right? Like right now it seems like an important technological achievement, but far down the future it'll all be washed out in some more significant milestones that we reach. So as we're here living it, yes, it's an important step. Each time they come up with a new chip design or a new kind of architecture, it is a necessary and important step. But in the grand scheme of things, it probably won't be remembered.
Yeah. Okay. Well, let's then warm up to what is more at the cutting edge of quantum technology, quantum computing technology, and where we think it could go. Let's perhaps set the scene a little bit from square one. At its most basic level, how does quantum computation work physically?
Okay. Well, that's it's a bit of an unfair question, I think, because we often have this expectation, and certainly the people within quantum computing that speak outside of our small community give themselves this gargantuan task of explaining something that took them 15 years of study to figure out in a matter of 5 minutes. Because this is not how we explain conventional computing. When someone asks how does your computer work, they tell you about how it's used and what it's useful for, right? They don't say, well, give me the physics of transistors. Which, by the way, if this was a technical discussion, you said, how does a digital computer work? I'd start with transistors and voltages and these sorts of things, because every single computing device uses the same technology. Whereas quantum computers, there are many competing proposals and existing prototypes, and they all work differently. So I can't just say, well, there's this physical thing in the world, and here's how it works and what it does, because each company or research group is doing something different. The one thing that they do have in common is a bit more abstract. So transistors, the reason, well, there's lots of reasons we use them, but the core sort of computational reason is because it's very good at representing a bit, a 0 or a 1. So in quantum computing, we need things that represent quantum bits. So these are like lists of numbers that can be 0, 1, and any other number, negative numbers, whatever it may be. So find a thing in the world that easily and naturally represents those numbers that you can manipulate with very high fidelity and finesse, and you have something that represents a qubit. And if you can manipulate that in according to a sequence of steps which change qubits to qubits, then you can call that a computing device. So it's anything that can represent quantum information and the sequences of qubits instead of bits, and can change that according to an algorithm, so a sequence of steps, is a quantum computer.
So the progression from going from conceptual quantum computing and maybe simulating quantum algorithms on a classical computer to instantiating them in the real world, is what you're saying that the biggest advance there is really an engineering problem? Is it developing these physical substrates to be able to represent quantum bits in the real world, or is there theoretical advance that needs to happen in order to get to quantum computing at scale?
It depends on like your precise definition of those words. I think at the highest level, we created these algorithms, and these algorithms are just steps to change lists of numbers to new lists of numbers. You could carry that out by hand if you wanted to. Of course, it'd be better if we built an automated machine to do that for us. And what we know from the theory of quantum physics is that there are degrees of freedom in the world, usually internal degrees of freedom of microscopic things that naturally encode information in that way. So if we can access those things and have control over them, then that's what we should try to do. So from a theoretical perspective, this was worked out, 100 years ago. But how to best do it, that's like a architecture design question, right? And that's a theoretical question that mathematicians tackle, people that have never touched a laboratory machine, and so they would call themselves theorists. And then, although the theory of quantum physics has been around for 100 years, actually applying it to materials, big things, is a difficult challenge, because we have to make approximations and models and algorithms that work on the computers that we have now to simplify things, and that involves a branch of, probably the biggest branch of physics, called condensed matter physics, which is really just the business of creating approximations to Schrodinger's equation that he wrote down in 1926. Though, again, those people would call themselves theorists, and it's their job to say, if someone says, here are the properties of matter that I want and need, and then those people go and try to design it from their understanding of quantum theory. Now, in some sense, we don't know which questions to ask, so it's a kind of back and forth between engineering and theory. So the engineers make some progress. They say, this sort of thing isn't working out. We need these new parameters. We need something with these new set of parameters. Then the theorists come and try to work that out. So it's a back and forth. But the basic theory is well understood. That's quantum physics. Nothing is going to change at the fundamental level in terms of quantum physics.
So then, if we had to take something like a problem like RSA encryption, and looking at the point at which something like that becomes essentially obsolete as an encryption method to be used in practice, what needs to be true for that to happen? How big does a quantum computer need to be, and where are we today versus that level?
So what we're trying to do is basically create what's known as a fault-tolerant quantum computer. So the actual quantum bits that will do carry out the computation will be virtual quantum bits. They won't be the real physical things, like real physical transistors. And you kind of encode these logical quantum bits redundantly across many physical qubits. And it really depends on how much error is going on, how many errors are happening, how much noise, how resilient your physical device is. That dictates the ratio of physical qubits to a logical qubit. So that, a typical number might be 1,000. So you need 1,000 physical qubits to create one logical bit that actually encodes the information in a robust way that it will last a long time. To crack a typical RSA key would require billions of qubits. So we're not there. We're not there yet. We have no fault-tolerant qubits. We have no qubits that we can do whatever we want with, and they'll last forever. We haven't created one of those yet. We're at the level of maybe 100 physical qubits, so not even enough to make one logical qubit. So it's a long ways away.
Yeah. Are you optimistic that we will get there in the foreseeable, or when you say long ways away, how long? What is your mental picture of that number?
Well, it's interesting. I think people, when we talk about like encryption and security and sensitivity of information, you should really quantify that in terms of number of years, right? So, does the secret I have, is it a 1-year secret? Is it a 50-year secret? I think for individuals, like your secret, probably, a sensible person would say that a secret is only it's only worth one lifetime. But, states have secrets too, so that they need to last beyond a lifetime. When we talk about quantum computers, that the time scale there really depends on the input into the problem. So the inputs that we need are basically boil down to money and people. So there isn't a magic number that says it's definitely 50 years away. It really depends on how many people are involved, how organized they are, and whatnot, and how much money is being put into it. So it really depends. I think I don't think that things will progress as they are now, because as we progress, things will compound, and as it becomes more interesting, more people will become involved. As it gets closer, more money will be put into it. So the things compound. If we try to extrapolate in the same way that digital technology progressed, then it'll grow exponentially in like some sort of quantum Moore's law. And then you can, if you make that sort of model of progress and say, we double the number of qubits that we have every year, then maybe it's only 25 years away. But if it takes 2 or 3 years to double, then that horizon extends.
Yeah, there are certain technologies that are sort of infamous for having this nature of being just around the corner for decades and decades on end, and some of them are still not here. Nuclear fusion, creation of synthetic life, things like that. But people have also been very wrong in the past. I think the famous example that comes to mind is the former president of IBM in the 1940s said that there was a global market for something like 5 computers, and it turned out to be outrageously wrong. I mean, I've got 5 computers in this room with me as we speak, and he was really just thinking, confined to the wrong paradigm and couldn't really see the full potential of what, personal computation could look like. And I do wonder if we're in a similar paradigm as it pertains to quantum computers. Do you think we might experience a similar phenomenon where at some point in the future quantum computation is everywhere? People have personal access to quantum computers.
Well, I think that nuclear fusion is an interesting example, and synthetic life and nuclear fusion are 2 completely different. Obviously, they're different things, but they're different in the following way as it pertains to like progress. Like synthetic life, I mean, we don't even know what life is. Like people argue about what life is, and so the problem is it's just too vague to say how would you even decide whether or not you achieved it. Whereas nuclear fusion, we've understood that for decades, and probably again the main reason why it's taken so long, and we're not quite there yet, is again money and people. But what is the purpose of nuclear fusion? It's energy, right? But it's so much easier just to dig up fossil fuels and burn them. There was never really, it wasn't necessary, necessary in quotation marks, right? There's no economic incentive or political will to make it happen. If you had put people and money into it, then we would have it already. The physics is very well understood, as opposed to synthetic life where we don't even know what question we're asking. Nuclear fusion is more like quantum computers. We understand quantum physics to a remarkable degree. We know it can be done. It's just a matter of putting money and people on it, and they'll answer the questions and solve the problems as they come along. There's nothing in the theory, and we're all going to assume that the theory is correct, that forbids this from happening. So that I think that's why it's inevitable. I really do like that quote. I use that quote quite often, but there is a sense in which he was right. There wasn't more than 5 of those devices, right? And if you compare quantum computing now to maybe what was going on in the 1940s in terms of classical computing, IBM sells a quantum computer, right? It's tens of millions of dollars. It has 27 qubits. There's roughly 5 of them, on the order of 5, and I would confidently say they're not going to sell more than that, right? So what happened, right, is that they didn't foresee basically miniaturization and the breakthroughs that came. Had he thought about it for a little bit longer and was convinced that it could be miniaturized, it could be deployed at scale, then he might say, well, yeah, sure, everybody might want spreadsheets calculated if it's cheap and free, right? So the same thing could be true with quantum computers. There's no theoretical reason why we can't solve the problems which currently confine them to laboratories and then put them in, a wristwatch or something like that. And so, we don't know what exactly those breakthroughs will look like. Just to throw an example out there, right? If you could build a high temperature or room temperature superconductor, then you wouldn't need these massive, basically refrigeration devices that hold liquid helium and cool some vessel down to colder than outer space. You could just put it out on the table, right? And that wouldn't really change that would be no different at a theoretical level. Like someone who thinks about quantum computing from a theoretical point of view, they don't actually care what it looks like and where it is, right? But it would massively change like how it affects society, because then it would be ubiquitous. So we don't know. Yeah, I mean, as it stands now, there's not going to be more than a few of them, because there's not enough liquid helium in the world to cool them down, right? But if we could do it without that, then yeah, they could be everywhere.
Yeah, it's interesting the question of why is it then that funding and minds are not focused on this issue and this technology as much as they possibly could. I mean, the example of nuclear fusion, I think you're right. Fossil fuels are easy to access, and I don't think we'll run out anytime soon. And so that makes sense. But if you look back at something like the Manhattan Project, there was a strong need, I guess, of sorts to create a very powerful nuclear weapon, and money and people followed, and that problem was solved. And with something like the classical computer revolution, the economic value, the impact to the world has been so enormous. It would be absurd not to invest in developing a technology like that. And then when I look at quantum computing, what is the difference? Is it that we actually don't believe that the applications could be impactful enough, or what is it that is stopping that flow of people and money into this technology?
Yeah, I think that people don't see a need for it, right? Even the most fantastical applications we can think of, right? That we can design drugs quicker, or create vaccines quicker. I don't think people actually really care that much about that. There seems to be more pressing problems. So I do think that that's currently what's blocking it, is that people can't see the desperate need for it. Right? We have computational devices. They work pretty well for all the problems we can, all the daily problems that we've given ourselves. But yeah, I mean, there's some companies obviously that are investing in it, investing at quite a high level, I would suppose, and they do see the need. But maybe we don't actually know the parameters, right? So suppose I said, well, we can solve all the world's problems, and all it's going to take is everybody has to live off food rations and work 16 hours a day for the next 20 years. But I promise at the end of that, we'll have solved all the world's problems. I still don't. Even if everyone believed that promise, I still don't think it would happen. So I think, yeah, it's with the Manhattan Project, and then with like the Apollo missions, which included like millions of people and trillions of dollars. It is those are interesting phenomena, right? That so many people got behind it, working towards the same goal. I don't think you can find that level of nationalism anymore. Certainly not in Australia, anyway. But yeah, there was I think probably a lot of competing incentives, and probably a lot of propaganda that an ethical side to it that would be more visible today. So yeah, I don't know. I couldn't put a number on it, but I would say that it's on the same scale in terms of need of something like a Manhattan Project or the Apollo program. That's really what we need to build a quantum computer, and we're not doing that today. On the flip side, imagine that we tried to land someone on the moon in the same way that we're trying to build quantum computers today, right? So a bunch of thousands of of professors with groups of 4 or 5 PhD students that are competing for a small pot of money, a few startup companies that put everything behind, patents and intellectual property, mostly vacuous CEOs with just big egos, and just a lot of money flowing around for completely vapid reasons. We would never have done it, right?
Yeah. I guess maybe then it comes to the question of what we think the applications actually are. One we've talked about is cryptography, but I think one of the motivations for developing the theory behind quantum computers actually goes all the way back to Feynman and his colleagues in simulating quantum processes, simulating chemical reactions. And I mean, when I just say that sounds like a huge application space. You can develop new materials. You mentioned condensed matter physics as one of the biggest areas of physics. This would have huge applications in condensed matter physics. So, I mean, what are the what is the scale of application? If we were to come to the point where quantum computers were a part of everyday life, how would the world change? What problems could we solve then that we can't solve today?
Well, we think there are applications for problems that we are solving, but not at the scale we think we might be able to solve them. So, we design materials, we design drugs by using our understanding of chemistry, sometimes down at the quantum level, but with approximations. So, we do this now, and we think that quantum computers would enhance these capabilities. In those areas, I think that it will move slowly. Like we won't notice like this. Like it won't be like a switch has been flicked on, and all of a sudden we'll be able to do something that we couldn't have done before. It'll be slow progress, improving upon things, and that will probably not feel as impressive as it is because everything is sort of increasing, right? Like all of our society and economy is built on this idea of constant growth. So we would expect it, demand it, and that's what will be provided. So as more of the same will happen, right? Like we're getting better materials, we're getting better medicine. We can create vaccines in a matter of months for new diseases. These things will just happen faster and at a bigger scale, but maybe the problems come faster too, right? And these two things can just kind of wash each other out. You can think of fantastical scenarios, but even with digital technology, which is completely revolutionized society as you live it, it's pretty mundane, right? What did we do with it? We created TikTok so we can look at each other with cat filters on our faces. So it'll be kind of boring, I think, but it will transform society, in kind of the same way that digital technology has. We'll live and work and play in completely different ways, but for the people living it, it will just seem like everyday life.
Well, let's maybe then move on to some of the more speculative topics in this area. I think quantum computing and really quantum physics in general is often subject of deep speculation and a generator of weird sounding ideas, which I know you're very intimate with, given your recent book, which I've just finished, and which I thought was very entertaining, and I actually, quite frankly, learned a lot from it. So I would recommend having a look. I guess one of the most well known among these, and something that you commented on your book, is the idea of a quantum multiverse, and quantum computing has been an area of physics, or an application area, that has actually generated some commentary on this topic. I would love to get your take on this idea of the quantum multiverse, and I have some follow-up questions, but I would like to get your unfiltered views to start off with.
I don't find it useful. I think some people, like one of the most prominent proponents of it is David Deutsch, who was one of the founders of quantum computing, and he likes to think about quantum computing as computations happening in, I don't know exactly how he thinks of it, but parallel worlds, whatever. But yeah, just because you use an idea or concept for something successful doesn't prove that it's true. So if he likes to think about it that way, then great. If he finds that useful, then so be it. But the multiverse and all its incarnations is not a testable hypothesis, and so it doesn't, for me, it doesn't seem like it's that useful of a hypothesis. If you like it, then by all means, create some part of your personal story which includes it. But if you find it useful, I think that in itself is an interesting research question as to why. But in terms of practical value, I think over the years it's shown not to have it. Otherwise, in the many decades since it especially in the context of like the many worlds theory and quantum physics, it would have been part of the practical side of quantum computing, which the vast majority of people who study and use quantum computing are practicing applied physicists, right? Who don't use this concept of many worlds to get their job done. And I think that that in and of itself shows that it's actually not a very useful idea.
Yeah, but I think David Deutsch looks at it more as a prediction of quantum theory. I think he points to, for example, Shor's algorithm for factorizing prime numbers, and he says if this was done in a classical way, it would consume more steps and more time than we have in the universe, and yet that doesn't happen. And he asked the question, where does the factorization happen? And it is a bit of an odd question, but his answer is it happens across multiple universes and collapses into one of them. How do you then think about that algorithm, for example, where it does use superposition as a superposition is the sort of underlying basis of that algorithm, and a collapse at the end to a definite answer. How do you think about where that calculation then takes place?
Well, as I said before, I can do the calculation myself with pen and paper. So in that case, where does it happen? I guess it happens in the combination of my mind and on the paper itself. And there's no, the collapse is something I do with a piece of graphite and and some fiber that's been flattened. So I don't know what I don't know how he would respond to that, right? It seems like a bit of a non sequitur to bring up a quantum computer when you can do a quantum computation yourself by hand. In the context of Shor's algorithm, like where does the factorization happen? Actually, it doesn't actually happen in Shor's algorithm, right? So Shor's algorithm is mostly a classical algorithm. Like if you put all the steps together, most of the steps are classical steps involving Euclid's algorithm for the greatest common divisor that was thousands of years old. So what actually is happening at the quantum part is it's just taking a function and trying to find a pattern in a function, and then once it finds that pattern, then it's kind of solved a sub problem in a bigger algorithm that's mostly classical. So you've designed this algorithm so that you've created a sub problem which the quantum computer is well suited for, and then Deutsch's other algorithm, like the Deutsch-Jozsa algorithm, the first quantum algorithm with a quantum speedup, was designed specifically to exploit the fact that there's interference when you do these calculations. The negative numbers cancel the positive numbers. So you can write this all down. Like if you had a big enough pad of paper, you can write it all down, and it's not happening in parallel universes. It's all on one piece of paper in this universe, in this one world, right? So I think it's a bit cartoonish. I often find it surprisingly. It's surprising how sticky it is. Like how given how cartoonish it is. It's a very it's not very deep, right? You just look at it and you think, oh well, look, I put the data in these terms, and then I put an addition sign between them. I'll interpret each of those as being in its own separate world. It's a bit, yeah. For me, it's a bit cartoonish.
One of the other phenomenon that David and many people point to is the phenomenon of decoherence, which is a big and important term in quantum computing. And I think many people, there are sort of two camps of people. I think some think of decoherence as the quantum system interacting with the environment and kind of collapsing to one state, or however you want to term that. And then there's the other camp who considers decoherence as the environment kind of getting entangled with a quantum system in superposition. And as you said, there's different terms. There might be a term for Matt and a term for for Chris in one state entangled with a quantum system. And they would then think of that as, Matt and Chris entangled with one quantum system, and then Matt and Chris entangled with another equally real quantum system. Both of those which have all right to be called, real and existing. How then do you think of what do you think of the concept of decoherence physically, ontologically? What is happening in decoherence?
Yeah. So if you take a system and it's isolated, then the Schrödinger equation is a very good equation to use to describe the behavior of that system, and if you make predictions based on it, you'll be right most of the time. If that system is interacting with another system, the mathematics of quantum physics force you to describe it in a certain way, and we give that a name. It's called entanglement. They just become correlated, and in the same way that classical correlations, render uncertain, some properties of the system. The same happens in quantum physics. So I don't think there's anything mysterious there. The decoherence and superposition itself is what we call in quantum physics basis dependent. So in some sense, a superposition is only meaningful because you define some preferred kind of states of the world. And I would say from the universe's perspective, that those aren't special at all. I mean, you just chose to say that, say, the alive cat and the dead cat are special states of the world. And so the superposition has some particular weird meaning for you. But from the universe's perspective, it's just another vector in this space of allowed vectors. It's not a sum of two things at all. It's just its own thing. So yeah, when you set up a model that includes the environment, in setting that up, it usually prefers some basis. So the environment is set up in such a way to prefer states of the system and create robust states of that system. So if you imagine like a dust particle floating around in a room, there's lots of air molecules around, and every time an air molecule hits the dust particle, it that air molecule now encodes the position of that dust particle. So position in space is this one of these preferred states, just because you've stuck the thing in this environment, which is constantly encoding and copying the position. And so when you put that thing in superposition of two position states, it will cease to be in such a superposition quite rapidly, because the position information is constantly being encoded and copied in the environment. Now, if you put it in a different environment, like some very non-natural environment that was more conducive to momentum, then superpositions of positions would be natural and remain, and then the momentum states would be the ones that decohere. So for me, it's all about the kind of environment that you're in defines what states of the system are robust, and that in turn kind of sets up this kind of artificially paradoxical situation of superpositions, because they're not common. And so when they do happen, when you try to engineer them, they seem unique and surprising, but that's only because of the context in which you've placed this system in.
So why is it that you think then that that this is such a divisive issue in physics today, both among practicing physicists, but also just among sort of physics lay people who know a bit, read a bit about physics, but are not actively involved in the research? Why is there such a strong dividing line today? What are we not seeing that's providing clarity here?
I think it's not that important of an issue for people to spend time thinking about, and I guess what I mean by that is it's so far removed from everyday experience, right? Like, resolving this question is not going to help you get a new job, right? It's not going to tell you where to invest your money, what you should have for dinner tonight. Like, your everyday concerns will never be related to the details of what's going on in this sort of part of the world so far removed from every experience and sensation that you can have. So from that point of view, it's just not important enough for people to devote a lot of time to. I guess I don't want to be too glib about it, but it would be hard for me to really think about what problems it would actually resolve if everyone came to an agreement about it. So it's this. It's kind of like fiction, right? There are unanswered questions about a fictitious world. People will, there's always room for interpretation, and so you'll get people arguing about it endlessly.
Yeah, we've seen that, and I think we've also seen, and this leads very nicely to your book, your most recent book. I don't know how many books you have, more than anyone has spoken to probably. But there is also that. But then there's also sort of deliberate misuse of quantum terminology, quantum ideas, or even not deliberate but naive use of these ideas. And you've gone through several of them in your book, Quantum Bullshit, which is good fun. Maybe let's start with the motivation for writing a book like that. What brought you to writing that book?
It was a combination of things. One of them was the fact that my other books, which are for children, seem to hit a lot of different audiences except one. So, obviously, kids have the book, parents have the book, grandparents. I've even seen sort of adults but science enthusiasts pick up a copy because they like the way things are explained in it. But the one sort of audience that I didn't it didn't resonate with was, like, say, the undergraduate physics audience. So, like, people in their late teens, early 20s, right in that perfect kind of age where you know everything. So I was missing that audience, and then there was a very sort of clear kind of moment in my mind that I remember. I was walking through an airport. I was actually going to visit the publisher of my children's books for a dinner, and I remember seeing the airport, one of these airport bookstores, and it had the top 10 books, and it was shortly after The Subtle Art of Not Giving a Fuck became popular, and then everybody put a swear word in the title of their book, and I thought, well, if I rename quantum physics for babies to quantum fucking physics for babies, maybe it'll start selling in airport bookstores, and young professionals and undergraduate physicists will buy it. And so I joked about it with the publisher, and they thought about it for a second. They said, "Yeah, that's not actually a bad idea." And so I thought, okay, well, I'll write a book with a swear word in the title, and it just so happens that there is a lot of quantum bullshit out there, so it wasn't that difficult to fill the book.
Yeah, I actually tested some of your claims by doing a Google search for quantum blank, and you're totally right. It is a lot out there. Why is it that you think that it is such a misused topic? You don't get, for example, statistical physics hype out there. You don't get random chemistry hype, but there is a lot of quantum hype, and it's certainly overrepresented in the general public, and it's certainly the most misrepresented sort of brand of physics that I've seen. What's your take on that? What is the cause of this phenomenon?
Well, I think, again, because it's so far removed from our everyday experience, it just leaves lots of room for interpretation. Mm-hmm. And so, people are aware that there's this theory of quantum physics, and it's very successful, and it purports to explain the way the world works. And it's about a hidden sort of something hidden from our everyday experience. Then you take something else, right, that seems to be hidden, but a part of the world, like love or something. So certainly has to be some mechanism there, right? Well, but it's not observable. It's clearly not explained by engineering or statistics or Newton's laws. What's left, right? So I think that's why, right? It leaves so much room for interpretation, and people don't have the time, obviously, to get an undergraduate degree in physics to understand the limits of its application. So it seems to be there free for the taking to apply to whatever unexplained thing that you want to interpret.
Yeah, and in going through sort of the research, I mean, you work in this field, so I don't think you would have to do all that much external research. But looking at what's out there and trying to diagnose, how much of this is just naive and how much of this is actually malicious intent, it feels like a big mix. Do you have a sense as to which side it skews?
Well, I think the vast majority, like if you just quantified the amount, the number of bits, like the amount of information out there, most of it would be just innocuous nonsense, right? Somebody posts some meme of, cosmic consciousness or whatever they want to think about in the moment, without any malicious intent. They don't really intend to deceive anyone. They're not selling anything. It's just a reshare meme that resonates with them, and because it has the word quantum in it, it sounds cool and exciting. That's the majority of it. Obviously, when things go wrong, then it gets more attention, and so yeah, you see more stories about the things that do involve malicious intent, but I don't think that makes up the majority of it.
Yeah, well, it's a worthwhile read. I must say, I did learn a bit, even though I've got a couple physics degrees and some background in it. It summarized things in a nice way, so I recommend it. The other sort of back to quantum computing, the other interesting thing you've worked on is you've written several books on education, and I know you're involved in a quantum computing education of a sort through a company called Eigensystems. Can you tell me a little bit about what you're doing there?
Yeah, so the company is a quantum computing education company, and our goal is to democratize access to quantum computing education. So we talked about briefly already these quantum computers that are for sale, like IBM will sell you one if you have a few tens of millions of dollars. But obviously not everyone can afford that. So what we wanted to do was provide the same sort of benefits of tangibility by creating a desktop quantum emulator that is accessible and affordable and would allow people to engage in new and more I think just engage in new ways with quantum computing that didn't exist before.
Yeah, and when you say engage with quantum computing, do you mean algorithm design, developing software? Is this something for developers to use?
Well, part of the motivation, was we thought back to the early days of digital computing and this hobbyist mentality, right? When you could buy like an Altair device and there was some instructions for how to use it, but that was it. Obviously you couldn't use that device to program a web app, but you could learn how to develop some computing skills by using that. And the constraints of it forced you to do interesting things, like come up with an operating system for it. So that's what we wanted to harken back to, right? This hobbyist mentality. Now, you can't develop, you can't use it to say develop more optimized subroutines to run Shor's algorithm, because as I said, you need billions of qubits, and we can't simulate that with conventional technology. And you're not going to be able to develop practical commercial applications because, again, it's a small scale device that emulates the industrial scale technology. But you could do the same things that hobbyists did with digital computers. You could create quantum video games. You could, create, quantum chatbots, right? Create your quantum game that runs in parallel universes if you want. So these are the sorts of things that you can do with it. It's not about learning development in the same way that you would learn development in a nowadays, like software development, where the point is to throw someone into a commercial setting right away, because we're still at a really fundamental level with this technology.
Yeah, great. Is this available? Can people check this out, or is this something in development? What's the status?
Yeah, so the status now is we have devices. We have more customers than we can fulfill orders for. They're kind of pilot customers at the moment. We're giving them to, say, other university professors. There's a couple sort of more hands-on pilot programs that we're running that are for clients that don't have any background in quantum computing. So we're testing how we can deploy these things in that context, what sort of support people would need if they didn't have a quantum computing background. The obvious application is for professors that are already teaching quantum computing that just want to enhance the engagement with students to provide them with something tangible. And where, so the stage we're at is really looking at getting some investment so that we can start to scale up and mass produce them, so we can start to meet all of the demand that we're seeing for it.
Amazing. Yeah, well, it's
so we're hoping maybe early next year there'll be a website up where you can put your pre-order in, and by mid next year we're hoping we can start to ship for every order that we get.
Fantastic. Well, I can retrospectively, once the website is up, I can add it to the the notes here.
Sure.
Let's to bring it to a close. I like asking my guests a couple sort of structured questions. And the first, I think, relates very nicely to the work you do. You've been involved in book writing, and I assume book reading and book gifting for many years. And one of the questions I love to ask is, what book have you most gifted to other people, and why?
Okay. Well, okay, this is going to sound a bit silly. It's one of my books, but because the publisher gives me so many, so I get them for free, so they're easy for me to gift. But the one I like to give away the most is called "There Was a Black Hole That Swallowed the Universe," because I think it's a really fun book, kind of to the cadence of "There Was an Old Lady That Swallowed a Fly," so it's very easy to read and fun to read to kids. And when I designed the book, I created a reverse story where, so the story is about a black hole that swallows up everything in the universe, and there's a story that goes in reverse that puts everything back in the universe, starting from the Big Bang. And that story is written in UV reactive ink, so you can't see it on the page, but if you shine a UV torch on it, there's a story that goes in reverse when you go back through the page. So I like giving that book away with a UV torch, and then if it's in the context of some event or something, then I'll sign the book with invisible UV reactive ink, and the kids really get a kick out of that. So that's the funnest one to give away for sure.
Yeah, well, definitely no need to be embarrassed for giving that away. I think that's unique. That's amazing. The next question also relates to young people. You've thought a lot about young people's learning journeys, both from a very young age, but also at undergraduate level and beyond. And I think many people, when they enter, these technical fields, they enter physics, it's in a very undirected way, and it's almost by chance they might end up following some route and go very, very deep. So my question is, to a young person, or potentially just any curious person wanting to explore these fields, wanting to explore physics in general, and not knowing where to start, what advice would you have for somebody like that?
Well, I think it would just be start. People tend to over-optimize, and you get this sort of sense of stagnation or paralyzation because you don't know if you're doing the right thing. Even today, the vast majority of things that I do are mistakes, right? If I'm writing a book, there's false starts. I have a folder called the bad ideas bin, and it's the biggest folder on my computer. So you just go, and then as you go, you come up with questions, and in some sense, like, you just have to trust the process. That they'll be interesting and useful questions, and they'll eventually lead you down the right path. And that process of making those mistakes will make you better prepared for the path further down. So it's necessary. So making mistakes and what seems like wasting time is actually the most useful and productive thing that you can do. So just get started. I find I don't passively learn information very well. It's the process of doing that allows me to understand the things that I'm working on. So a lot of that involves writing and attempting to teach it to other people. Even if it's just the void. I post a blog post. That process of at least attempting to teach it to other people is what provides me with understanding. So that would be my recommendation. Just pick something. Just to try to write it in your own words. Right? Write it as if you were teaching it to someone else. Whether or not anyone else is going to read it, it doesn't really matter, because that process is what will provide you with the understanding.
Yeah, fantastic. The last question I have, we talked a bit about the advances in technology and in quantum computing, and one of the other areas that's also hyped up a lot, but is also bearing fruit, is artificial intelligence. And something you hear a lot of is the prospect of general artificial intelligence, or an artificial superintelligence. And my question to you is, suppose one day we were to be visited by an artificial superintelligence, and we had to pick one person, either past or present, to represent us to this superintelligent other. Who would you pick?
I feel like realistically, what would happen would be, some organization would create some sort of program of dubious ethical procedures that trains someone to be the representative, right? I think that sounds a bit cynical, I suppose. And if you're cynical about AI, like this, so your picture of a general AI or a superintelligence is like the Terminator, then probably you would want the inevitable to be over as quick as possible. So you should present like the worst example of a human, just so that you get it over with as fast as possible. So I don't know, Tom Cruise, I guess, or insert the political leader of your least favorite political party for the listeners.
Yeah,
I think I don't. Again, this is sort of this idea of like a singularity where the progress in technology will see some giant step transition. That's not usually what happens. So I don't think that will happen with AI either. So I'll give it so I think it's a bit absurd to consider, but so I'll give you my final absurd answer, which is Tommy Wiseau.
Fantastic. Okay, well, I won't open up this rabbit hole of Tommy Wiseau and whether we'll hit AGI, but it's been a fantastic conversation. Chris, thank you so much for speaking with me today.